Hello again. This is kind of a follow-on from a previous presentation I did about a month ago, where what we think of as constants, numeric values that don't change. As we advance our observations and our science, we realize what we thought was a constant is only a constant under certain circumstances, but it's actually a parameter, something that has multiple parts to it, not just a number. So, what is a constant? Kind of as the name suggests, it's something that's unchanging in its value. It's a constant value. The International System of Units, the SI, they make considerable use of agreed constants, not like a constant that is only a particular value in the physical world. They actually count things and then they agree on a particular count representing that constant. So, for example, what is 1 second? 1 second is 912631770 oscillations of a particular isotope of cesium. It's cesium 133. And they count the number of these oscillations. And when they say, we've got this many of them, everybody agreed, well, that seems to be 1 second. That's where it stands right now. 1 second is defined as the number of oscillations of a particular isotope of cesium. And then you say, okay, how long is 1 meter? Well, if we know the speed of light in meters per second, then we can get seconds per meter, and we can figure out how many of these oscillations mapped inversely on 1 second is 1 meter. So they're measuring a meter as a unit of time. And then the speed of light is, of those meters, how many meters per second or meters hertz? And it's, again, an arbitrary number. Now, the thing you'll notice about these is they all end without a fractional value. They're very large numbers. Even when they're inverted, they're still substantial quantities of digits, and they have no fractions. If all of a sudden we find a higher resolution way of calculating the duration of 1 second, it would still be exactly this much time, even if we can measure it to a much finer degree. But internationally, arbitrarily agreeing upon these quantities is the basis for all the constants. They moved from things like a platinum iridium bar of a certain length, or a kilogram is a sphere of a certain size. And they said, well, all those things have too much natural real world variability in them. But if we can agree to a count, to a numeric count of occurrences of something, now we have a basis where everything can be based upon these constants. The one constant that they're really relying upon is the speed of light as being a constant, because you can see it's meters hertz, and that gives you speed of light inverted as 1 second. And then 1 second is seconds per meter. And then 1 second itself is number of things per second. So they're very heavily relying upon the duration of 1 second and the speed of light. And we'll get into, like, that was really a good thing that they did to move away from physical objects. But there's a problem. They extended it. They said, well, if it's good for these other things, then we're all basing it upon these constants. But then they took it another step and they said, let's find a way to make all of our other extended constants based upon this same root set of constants. The ampere, the unit of elementary electrical charge, they divided that up and said, well, it's this many ampere seconds is 1 ampere. If you're into electronics, you know that you can relate amps to volts to watts, and that's just, relative off of one another. But then they took it out to temperature. Temperature, from a physics perspective, is best measured as Kelvin, but then they based it upon a quantity Boltzmann constant, but you have to be near 0 Kelvin in order to count this. They counted it as basically a quantity of energy force over time. So you can have joules Kelvin. And when you break that back down into what is a joule, what is Kelvin, you get meters squared, seconds squared, Kelvin. But it's all rooted in seconds, because meters squared, seconds is that prior unit, and meters is also based upon seconds. All these things are based upon essentially 1 second and the speed of light. eliminating physical items in favor of arbitrary agreed constants, that makes sense. The gorilla in the room is the drawback that everything is based upon the speed of light being a constant. And notice that if all of a sudden the speed of light is not a constant, that a number of these standard units of measure that are based upon the presumption of light in 1 second, you can't use them as a constant anymore. They have to be a formula for them. Second is agreed quantity of occurrences per second, and distance is a length per agreed fraction of 1 second. So there are other constants, and there's one of them that is astrophysical in nature. And it's called the cosmological constant, or lambda. It's a lowercase Greek letter, lambda. It's sometimes referred to as Einstein's cosmological constant. It's essentially the rate at which the universe is expanding. And there's this thing called the Hubble constant. And the Hubble constant is this number that comes up in the crises of cosmology. And it's a particular value, but it makes use of kilometers, seconds, speed of light. And if that number is based upon that set of units, then anything that would change those from constants to formulas or parametric values would also necessarily affect other things that are constants. So why the universe is expanding in the first place, the dark energy, that's another topic discussion. The expansion has generally been agreed in most scientific circles to be accelerating. It's not just an acceleration, it's a changing acceleration. It's an increasing acceleration. The acceleration rate itself, Hubble constant, was perceived as a constant. But now we realize that the expansion accelerates over time. Acceleration of an acceleration is something jokingly referred to as a jerk. But that's just another measurement of units of measure in physics. And I did speak about this late last year about constants being actual variables. So where it comes down, where like the rubber meets the road, is the cosmological constant, lambda, in most recent observations, and this is a report that just came out March of 2025, the group called DESI released their report called DM2, and they did the statistical analysis of their observations, which is thousands of galaxies, and they have a significance of 4.2 sigma. Sigma is lowercase Greek letter, sigma. It indicates the statistical significance of whatever your observed value is above background noise. And when they get to 5 sigma, it's kind of saying that's really what's going on. They're not quite there yet. As they expand things out, they find that the end result favors lambda as being not a constant, but a variable over time. And initially, they thought it was just time that varies lambda, but time over distance over long enough periods is also a factor. But remember, lambda was supposed to be a constant. Originally, it was a velocity, and then it became an acceleration, and then it was supposed to be a constant acceleration. And now it's a variable acceleration, or a jerk. Even the value of that variable has changed over time. When the universe first started expanding, it was a particular acceleration rate. That acceleration has changed over time and includes something called, recently described as, oscillations of baryonic matter. This is basically when the universe transitioned from hot, dense plasma that basically stars couldn't shine through, that the radiation pressure of the light from the stars actually pushed on the plasma and formed plasma bubbles, where the plasma was pushed out from the center and it formed spheres of increased density material. And we find that that's where galaxies have formed. That's a different discussion as to why all of that, but the fact that things got pushed out accelerated them. So the early acceleration may have been faster than the current acceleration. Rest easy, science community. This is not going to change things dramatically overnight. It's a small difference, and it's a difference that is from billions of years ago and many millions of light years away. So it's not something we have to change our math on Earth today for. There have been bigger upsets in the astronomical community in the past, like going from a flat Earth to a spherical Earth, or going from Earth-centric to heliocentric, or Milky Way not being the only galaxy, or there being exoplanets, or Earth-sized exoplanets in the habitable zone. Those were all much bigger disruptions in what we believe the universe is all about. But it's more like the difference between Newtonian and relativistic physics. If you're measuring a velocity that's relativistically speaking slow, nowhere near the speed of light, then Newtonian physics works great. But as you go faster, you may have to take into account some relativistic expectations, like when they did GPS satellites in orbit around the Earth, and they found out that they were off by more than 75 feet from real accurate location of latitude and longitude. And then they went back in and said, oh yeah, the satellites are moving about 9,000 miles an hour as they're orbiting the Earth. So if we take that into account as time dilation, then the signals coming down to the Earth are shifted. They're basically Doppler shifted by the movement of the satellites. And once they took that into account, oh, now we're well less than 75 feet, more precise accuracy. So sometimes you do have to take into account other things that you might not have thought of originally as other than a constant. So the lambda relates to lambda cold dark matter. This is how we perceive the expansion of the universe. And if you get to scales of 1 billion years or more and distances of greater than millions of light years, then the numbers start to diverge. And that's where the DESI observations are looking at. They're looking farther and farther back. And the nearer stuff, the slower stuff, that matches our lambda-CDM calculations. But outside of that, and there's a divergence, and that's the crisis in cosmology, as they say. But as you get farther and farther back, farther and farther away, the values of the observations tend more to match it being not a constant. What's the harm if all of a sudden the speed of light under certain circumstances is not that same constant? It's a different value. Then, we'd have to take all these other things that are based upon the speed of light, the duration of a second, distance of a meter, all that kind of stuff, the distance, the electrical charge, the temperature. Basically, you have to put a little asterisk next to that constant value and say, under certain circumstances. And then you give a parametric formula for how to calculate it under other circumstances. But it's okay for under most circumstances, just like Newtonian physics works under most circumstances. The speed of light could still be perceived as a constant, except when you get beyond these limits, and then it takes a plus or minus this or times that or divided by whatever, but it's still the speed of light. So it's referred to as the Dark Energy Spectroscopic Instrument, or DESI, and it basically looks out into space and evaluates the spectroscopic nature of the light coming from distant quasars, specifically galaxies that have an active supermassive black hole at their core, and it's sucking in material and spitting out light. And then we do a spectroscopic analysis of that, and we measure this as those galaxies are farther and farther and farther away. So that's where we see that our observed value for many thousands of galaxies is starting to diverge from what we thought of as a constant. And as I said, it's purportedly due to something called baryonic oscillations caused by reflection pressure plasma bubbles in the early universe. These plasma bubbles started out at about 1 million light years in diameter, and they have since expanded to about 100 million light years by today's observations. And if you ever see a picture of a 3D model of the universe, you'll see the galaxies are all lined up on these things they call filaments, big holes. And then on the edges of the holes, you see that's where all the galaxies are. These big open expanses are literally the bubble of that early plasma still continuing to expand outward. And that's part of the acceleration, is you have to factor in the bubbles. But I thought, well, if that's the case, then maybe we should look at it from a different perspective. We've got these things called gravity waves nowadays that we measure, and photons are known for having a wave-particle duality. Depending upon the type of observation you're making, you can measure a photon as a wavelength, as a wave. Gravity waves expand and contract space-time, so plasticity of the fabric of space-time. It doesn't change a specific distance. It changes all the internal distances of things. So it's not just like neutrons and electrons separated out. No, it's more like the atoms between components of a molecule separated a little bit. And when you do that over a very large number of them, you tend to get stretching and compressing of space-time. But what they found out was by differential tunnel pair length at LIGO, the Laser Interferometry Observatory, there's one in the northwestern part of the United States and one down in Louisiana, so they can compare notes, these giant L-shaped things. And one tunnel will be suddenly a little longer than the other tunnel, and that gives them a differential, and that allows them to detect that there's a gravity wave and it's moving in that direction or that direction. And by having two of them at different angles, they can see what direction the gravity wave was moving through. But the way they measure it is they take a laser and they split the laser beam and they send it down two different tunnels. The laser goes to a mirror at the far end, bounces off the mirror, comes back through a beam joiner, and then gets sent out to a detector. If the laser beam is precisely tuned, then if the tunnels are precisely the same length, you send it down this way and you send it down 90 degrees that way. When the beams come back, they'll cancel each other out perfectly and there will not be anything detected. One of the ways in which you can make sure that happens is that by using lasers instead of just light, lasers have this property called coherence. That's where the waves of the laser, the photons being produced, are all in alignment. So when the laser lasers or switches on, then all the light waves going down this tunnel and all the light waves going down that tunnel are phase synchronized. If the gravity wave rolls through, one of two things can happen. The distance from that beam splitter to the end mirror in a tunnel can expand and contract. And if that's really what's happening, the way you measure it is, well, the photons going down that tunnel will go out of phase with the photons going down that tunnel, and you'll get a detection. Or it could be that the wavelength of the photon itself stretches. And if it does stretch, that means that the color would have to get a little darker. Let's say they're doing infrared beams, which they do use infrared lasers. If the beam stretched the wavelength by way of the gravity wave, then the wavelength would get longer and the frequency would change, and therefore the color of the light would get a little darker, deeper infrared. But if the photons aren't actually coupled to the physical space-time, then the mirror moves, but the photon doesn't change its wavelength. So it stays whatever color it was. So you've got two approaches here, and you can see them on the right. Prior to the gravity wave, the in-phase waves of photons are hitting the mirror and bouncing back. You can either have, in the presence of the gravity wave, the mirror moves in both these instances, but what happens to the wave of the photons? Do the photons stretch? Or does the mirror move and the photon stays its same length, and now there's more distance from the last photon before it hits the mirror, and therefore there's a difference in the interferometry, and that's how you do your detection. Anchored or unanchored photons, that's a question. If it's the last one where the photons are not anchored and the distance changes, then that means that to get the same result, the speed of light has to stretch or contract. LIGO itself doesn't measure the speed of light. They're working off of a constant system, and all they're counting on is the interferometry distance between the two tunnels. If at some point during the gravity wave effect, they also measured the speed of light or the light distance down the tunnel, not just the difference, but the actual light distance, they may find, are photons anchored to space-time or not? So let's say they go one way or the other as anchored or not. Think about the background gravity wave. If the speed of light is not a constant in all space-time, all conditions, then the background gravity wave should change the speed of light from the constant value we know about it to a slightly different value. It's not going to be enormously different. It's going to be very short duration because the gravity wave just rolls through. It's going to be a very tiny effect, and it's going to be based upon the frequency of the gravity wave. So the higher frequency gravity waves are shorter. They're going to have less of an effect. But if you have very long gravity waves, the very long gravity waves are going to have a more pronounced effect, but the amplitude difference will still be tiny. At some point, I think that they'll actually measure the speed of light variation in the presence of gravity waves as a numerical quantity. And they'll say, well, if we got a gravity wave with this frequency, then it produces this variation in the speed of light. If not, then it changes this way. I think where we'll actually see this to be something that's obviously noticed is as we move from cesium particle fountain clocks to quantum clocks, that's another topic, quantum clocks, the number of fractional digits of resolution gets to be about another 3+ digits. And that will now take us to a higher resolution for what a second is. At that point, I think they might be able to see some variability in what 1 second is or what the speed of light is. If they did confirm that under certain circumstances, a slight variation in the speed of light, or c, then they'd have to include a little caveat in all those SI units and say, when not in the presence of a gravitational wave of a certain kind. Some point in the not too distant past, the National Institutes of Science and Technology actually had a disbelief in something that's now fact. That is, they had their atomic clocks sitting on a shelf in a rack, and if the clock was at a different height in the rack, time would be different by the very last digit in that fractional value, the number of impulses per second, off by 1. And they didn't believe that was the case. How could gravity have an effect on something so small that is such a high count? And so they realized that, well, Boulder, Colorado is about 5,000 feet higher off the surface of the Earth than is Maryland over the East Coast, because the two places that they had their atomic clocks were Maryland at the NIST headquarters, and then where the WWV was in Boulder, Colorado. Difference of about 5,000 feet was enough to cause a variation in the accuracy of time of day. And then they figured it out and they realized, oh, it's the Earth's gravity. The farther you get from the Earth's gravity, the less the effect is on the particles in the particle fountain, and therefore you can count, and the duration of each count from where it gets emitted from the atom until the detector picks it up is affected by gravity. So now they have, wherever they have racks of time sources, they have at least 3 of them, and they're separated by distance. So they can actually average within a rack multiple clocks, and they can average Boulder, Colorado versus Maryland. When something first comes out, it can be incomprehensible that it's not a constant. And then you find out it's actually not a constant, but you can adjust. So in summary, it all comes down to when a constant is a constant, or a constant is only a constant under certain circumstances. Otherwise, you need a formula with a couple of parameters in it. As we find out, it may be something like time or distance or in the presence of a gravity wave of a certain wavelength or frequency. So if a gravity wave stretches and compresses the fabric of space-time and it affects photons as waves, then maybe it's not a constant if in the presence of a gravity wave. And so just some science that has to be done. But the result of the speed of light not being a constant depends upon the circumstances. The most prominent circumstance for evaluating it not as a constant, but as a parameter would be in the presence of low energy gravity waves that extend over long distances. But in general, no biggie, doesn't make that much of a difference. But lower frequency, longer wavelength gravity waves, it'll still have an effect, but it'll still be minuscule. But we might not actually be able to detect it and evaluate it digitally until we go up to the next higher accurate clocks. We go from cesium atomic particle fountain clocks to quantum clocks. Think about that for a moment. The speed of light not being a constant under certain circumstances. And to back it up, we have lots of links. And if you didn't know what the lambda-CDM was, there's information on that. And if you don't know about the whole wave-particle duality thing, some background information on that. And what LIGO is, if you haven't heard of LIGO. Comments? Questions?
Very nice.
I don't think it will be earth-shattering for the speed of light to not be a constant under all circumstances. But to date, the speed of light has always been defended as a constant under all circumstances. And, having LIGO and saying, well, I know the mirror moved, but did the wavelength of the photon stretch, or is it decoupled from that? Because we know that there's these thing called Einstein lensing or gravitational lensing, Einstein rings, whereby if you have enough gravity, you can actually bend space-time, but light still travels along that bent space-time. The light itself doesn't change. The space-time in which the light is moving changes. So that kept us like, yep, speed of light's still a constant. And the old Einstein adage of, if I have a guy on a train and he's got a flashlight and he shines a flashlight out the front of the train, the light in the photons of the flashlight, those are going at the speed of light, even though he's going at the speed of light. It's not the speed of light squared. It's still the speed of light. And a lot of people have difficulty grasping with that. Well, it's got to always be a constant or else a lot of things break down. In this particular case, there's nothing that's going to break down because the differential is so small, but to ignore the potential for the differential is just not thinking.
Yeah, it's when you talk about it's just like the less fractions, and then for everyday calculations of position of satellites or for, atomic clocks or anything that is like mundane or everyday life, it will not affect us. And then to teach physics for high school and even college, I don't see any problem to start the calculations mentioning as a constant, that most of the calculations we do as taking as a constant. Now, that is the caveats of extensive gravitational fields like large objects or a cluster of galaxies, or now the new part that I'm still learning is about how much gravitational waves change the path and change the speed and alters because like you said, when we calculate, that calculation is in space-time. So if you're stretching space-time, the constant is, the light's still moving in the same speed. It's just that we are catching the emission a little bit later because the space stretched, it changed the wavelength. And so it's kind of hard to put your head on it. It's even to teach that is very complicated. By the way, I only learn a little bit more because I had the opportunity to teach about it. And the kids' questions plus my information that I'm changing and reviewing helped me to get like a little bit better of the picture. But it's very hard for us to understand because it's like when we say, "Oh, this makes no sense." You have to imagine that we are locked in a body that has very little senses. We are blind species. We don't hear that much about nature. Like our senses are so limited that most of the things make no sense, and it's hard for us to catch how people know those things about physics. How to you explain? How to find analogies to explain? It's really hard. And so, yeah, like for most of the calculation that we do, even like in when you study beginning cosmology, you take light as a constant because this is such a special uh like little details when you're doing like high particle physics and postdocs and those very complicated publications that then you can mention that it's would be a constant, but it changes in special situations.
From what I know about LIGO, the reflected photons that go back through the beam convergence do not change wavelength. They start out as in-phase photons from the lasers. They reflect off the mirrors, and then they come back. And if one tube is longer than the other one, that's how you get your interferometry difference, not because the wavelength changed, but because the arrival time of the previously in phase photons is now out of phase. And so that's how you get your difference of your interferometer.
What was the publication that you read about the coupled and the non-coupled photons?
I was reading how LIGO works and the efforts they went to get the beam columns evacuated, vibration isolated, and the mirrors and how they had to hang them on quartz fibers in order to make it where they wouldn't sway in the presence of the reflection pressure from the higher power lasers and all this minutia that you won't find covered in your average PBS or YouTube video regarding LIGO. There were some factors that they really had to consider. The wavelength of the returning photons was never something that was different. So if the length of the tube stretched and made the mirror be farther away, now the distances we're talking about here is
The
fraction.
size of a proton.
No, they're now down to a fraction of the size of a neutron, the diameter of a neutron. So this is infinitesimally small distance movement of the mirror of one column versus the other. And that's how they do the interferometric differentiation is by, the photons coming back to the beam convergence out of phase, and therefore they didn't cancel each other out. They were slightly overlapped and therefore would not cancel each other out. And therefore you have a brightness going into the detector. But the wavelength
but
didn't change.
that's the regular detection, the normal detection of LIGO and all the other equipments that work
Yeah.
like this.
Yeah.
It's just that a stretching of space-time changes the arrival time of and then decouples the cancellation. Now, what I haven't read is what you mentioned of, the the beam being stretched and changing wavelength. I haven't read that one
It didn't.
before.
It didn't. So if the photons are not coupled to physical space-time, then when the distance changes, the wavelength will not change. And that's what they see. They don't make a note of it. It's just like the laser goes out with a certain in-phase wavelength. And when the beam comes back, it's not that the wavelength changed, the phase changed. So their detector is in the same wavelength as the source beam, which means when the mirror got farther away, the photon's wavelength did not stretch, which meant the photon was not coupled with the physical space-time that the mirror was coupled to.
Okay, so, but you mentioned that, that would be a possibility to be coupled and change.
Yes,
like you mentioned,
you have
two
two
things.
approaches. Either the
Yeah.
photons are coupled with physical space-time, or the photons are decoupled from physical space-time. And I think what they're seeing is when the mirror moves, the photon wavelength does not change. Therefore, the photon did not stretch. Wavelength didn't change.
Mm-hmm. But you
Therefore,
mentioned that would be, or that would be just a supposition, or just a postulation.
it would change the speed of light from a constant to a calculation based upon the fabric of space-time that the photons were traveling through. Now, the normal state of speed of light is an unimpeded photon. You always see it described as the distance a photon will travel in 1 second if the photon is not impeded. It doesn't go through anything. It doesn't reflect off of anything. It doesn't have anything affect it. It's like you didn't touch the photon. It just went through. And after 1 second, it traversed this distance. And if you inverse
But
that,
have you read anything about photons coupling with space-time?
no, I look for that in the LIGO material, and LIGO doesn't even touch on it. They do
Okay.
state that the wavelength is the same. If the wavelength is the same going out and back, and the only thing that they
Maybe it's
use,
because the change is so minimum that they cannot detect.
well, that's why I say maybe we have to get to quantum clocks where you get one more digit in the accuracy.
Mm.
But I also think it's
Because
just
then
because,
getting one more digital of the accuracy on the second actually adds accuracy in all the other measurements of
yes,
the
yes.
SI.
Yes. And that's why
Like
NIST is,
every addition in one thing, like if you get more the mole more precise or the
mhm.
second more precise, you have a cascade of more precision measurements for all the other forms of measurements.
Yeah,
That's kind of cool.
the SI constants are all integers. They're not fractional. They're counting things, and they define this as a certain count of things. If you can now measure it more accurately, it doesn't change the count. But if the count defines time and the amount of time it takes for a photon to traverse a distance that changes is going to take longer time fractionally, by how long does it take a photon to traverse half the distance of half the diameter of a neutron? A very small amount, but you're not going to detect that small amount by having a clock that's
I
not
find it
accurate to that moment.
incredible that we can measure something like that. It is crazy.
It took them a long time.
We are about picosecond, right?
No, attoseconds.
Oh wow.
Yes, yes. We're down to about 60 attoseconds, ATTO seconds.
That's crazy.
Now, a nanosecond is a billionth of a second. A picosecond is a thousandth of a billion. And then a femto is a thousandth of a pico. And then an atto is a thousandth of a femto. So that's the kind of scale we're talking about here, is about 60 attoseconds.
And those kinds of measurements we are talking about is mostly for precision measurement of quantum computers or measuring
No, that was
the width of atoms or
no, they
working with like very minimal small things that are mostly quantum by the time
no,
and size.
there's two purposes that I've seen for attosecond measurements. One is they do a reflection reference off of electrons and photons moving within atoms. It's a very, if you're into the minutia, that's a very fascinating thing to see. Is we used to think of when a photon encounters an atom and it causes an electron to become energized, move to an outer orbital, and then move back from that outer orbital to a more grounded state and emit a photon. That's not instantaneous. When you can measure time down to 60 attoseconds, you can actually see the photon come into the atom and then energize the electron, and the electron accelerate to an outer orbital. The electron pauses. The part that they want to get down to the less than 60 attosecond level is they right now don't know whether the photon comes out when the electron pauses at the outer orbital or when the electron starts to accelerate back downward to a ground state is when the photon comes out. So even now they're like, we want an even finer number. But the
That's
the other
crazy.
thing that they use it for is laser weaponry. When you're putting out a laser beam at 50 kilowatts, if you leave it on too long, you're going to vaporize your laser with the amount of excess heat. The way that you can reduce the amount of waste heat in your laser is by leaving the beam on a very, 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 very short period of time. So what they do is the laser is switched on and off, like even in odd attoseconds, to make the beam come out. So from the human visual perspective, the beam is just like beam on. No, the beam is like on, on. And that's how you
Yeah.
get the waste energy down to the point where it doesn't melt your laser, is attosecond beam switching.
Remember that we filmed us pointing a laser to a solar cell
Yes.
and putting a speaker and make like a very high pitched noise.
Yes. What we found out was the power source of the laser was a battery, and batteries, depending upon their load and their current charge level, can produce a different voltage. But LEDs work best at a variable voltage, but a constant amperage, a constant wattage for the laser. So it's called constant current variable voltage. And the way that they do this is they have a little oscillator in the laser pointer that to keep the beam power a constant, to make the beam look like it's not getting brighter and dimmer and brighter and dimmer. They have a constant power source and they switch it off and on at a very high frequency. And as the beam stays on longer, the waste heat of the beam starts to heat up the laser and affect its power efficiency. So we would shine, usually my blue laser beam, which is about a watt, shine that into a solar cell, and then the solar cell voltage output would go to a speaker, to an amplified speaker. So you could actually hear from the light going into the solar cell producing a voltage, and then the voltage producing an audio detectable sound. You could hear the encoding of the laser beam switching off and on. And the longer you left the beam on, the higher the frequency of the oscillation of the beam power would be. And it would get so high that it would hurt your ears. It'd be such a high frequency. So we would turn the beam on, and when it got to this squealing level, turn the beam off before people start, complaining of blood coming out of their ears or something.
Yeah, especially if we're doing a public park.
Any more comments about tonight's presentation?
Nope.
No. Thank you.
Okay, let me stop recording.